Spectroscopes. What these do is they take white light and they break it up into all of the different colors that are actually creating it. Because white light isn't actually white. It's like a bunch of different colors, but your brain doesn't know how to process them all at once, so it just tells you that it's white. If you have a spectroscope, this breaks that white light up into all of those different colors, and then that's how you can see what the light is actually made out of. We have spectroscopes at the school, but I don't have you at the school. So if you want to make your own spectroscope, I have a really good video for how to do so. I'll post that as an optional thing. But question is, why do we care what colors the light is actually made out of if we can just see it and see that it's white? Like, why bother with all this? And the answer is that different elements have different colors of light that make them white. So let's say we're looking at hydrogen. Hydrogen has those three lines right there. And what that means is that when you look at like hydrogen, if you had a hydrogen light bulb, it would look white, but it's actually an average of those three right there that would give you the white that you see. Then if you looked at helium, helium's got a whole bunch of these, but it would also look white. Oxygen, same thing. As we move down, we start to see more and more. The reason why this is useful is because let's say there's a planet that we can't actually get to, but we want to know what it's made out of. Does it have an atmosphere? Is there oxygen on this planet? What we do is we take our spectroscope and we shine it at the white light that we see coming from that planet, and it will tell us, okay, that white light is actually this, I shouldn't use black there. It's actually this average of different colors. It's not actually white, it's actually, all of these tells you that there is oxygen on that planet. So it's a super useful way to figure out what things are made out of if we can't actually get to them. Last thing to talk about is the Doppler effect. So if you've ever been like standing on a sidewalk and a car goes by with its horn on, or like a fire truck with sirens, or if you've watched Big Bang Theory where Sheldon dresses up as the Doppler effect for Halloween, basically what's happening, first of all, this is a typo. This should say blue, and this one should say red. What's happening with the Doppler effect when we talk about sound is this ambulance is sending sound out in all directions. But it's kind of catching up to the ones over here because it's actually driving towards the sound waves that it sent out in that direction. So these sound waves end up compressed together, which means, remember, shorter wavelength, higher frequency. This is the more energy version of a sound wave. If it has more energy, the way that we hear that is with a higher pitch. On the other side, the ambulance put out sound waves over here as well, but it's running away from them. So they're kind of getting spread out. And so what that does is it lowers the pitch, because you have to have a longer wavelength than we would have had over here. So lower pitch for when the ambulance is going away, higher pitch when the ambulance is going towards us. And that's how we hear it with sound. But light is also a wave. So if we want to talk about the same thing, how would that happen with light? Let's say this isn't an ambulance anymore. Let's say that this is now a light bulb. And so this light bulb is putting out light in every direction. As the light bulb catches up to its own light waves that it put out, it squishes them together. So let's think back to our spectrum over here. On the ultraviolet end, this is where the waves are really close together like that. And on the red end, this is where they're really spread out like that. So if we've pushed them together like we've done over here, that means they look more like this than they actually are. So if we started out with something that was right here, and then we squished it together, that's going to make it look a little bit more like blue. On the other end of that, let's look at this guy over here. Yes, this light bulb put out waves, but then when it was running away from them, they're kind of getting stretched out. Stretched out, we're thinking like, that's the really long waves over on the red end. So if we started with this same wave of light, it's shifted more towards the red side. Okay, let's tie this all together. If you didn't entirely follow that, that's okay, because this next part is the key takeaway here. We've said on the previous slide that we can figure out what a planet is made out of with spectroscopy. And then what I'm telling you right now is that we can figure out if things are shifting one way or the other based on whether or not they're going towards us or if they're going away from us. So in this example, all of these arrows tell you that we have shifted towards red. So we've shifted more towards the stretched out wavelengths. The way for that to happen is if the thing is moving away from us. And the reason why that matters is, let's say there's a planet that we know has oxygen on it. And we see all of these lines that should match up with oxygen, but they've been shifted over just a little bit. We know that that oxygen must be moving away from us. And that is why all of those lines shifted a little bit. And if the oxygen is moving away, that means the planet must be moving away. So we can tell the planet is moving either towards us or away from us based on which direction we are shifting towards. So that is how astronomers know that the universe is expanding, is because they can see things that are redshifted, meaning that they're being stretched out, stretched away from us. They're moving away because space is actually expanding in between us. Okay, here's some stuff for your study guide. You should be able to tell me all of those things by now.